I will be giving you a short review, again from a physicist's point of view, of linear algebra first. And I'm hoping to do most of this today. I will go through the definition of a linear vector space. We'll talk about bases, operators, and things like that. Then tomorrow, hopefully, we can discuss a bit more about abstract algebras. And finally, we will get to group theory. There I will mainly talk about finite groups, such as the permutation group, and a little bit about SO3 and the Lorentz group. And then Freddy Cacciazzo next week will go on and talk about Lie groups and Lie algebras. Okay, so let me start straight away with the definition of a linear vector space. And let's choose a very common example from quantum mechanics, your Hilbert space. What is a Hilbert space? It is a set of all the physical states in a quantum mechanical system. So I will be using Dirac's notation and use psi to denote all physical states. Now, what do we mean with H being a linear vector space? And I should say this is a linear vector space over the field of complex numbers. It means that if we take, I will need 3 states that are elements of H. So I will be using phi, psi, and chi. And I will be also needing some complex numbers, let's say A and B are complex numbers. So it means that if, say, phi and psi are elements of H, then a combination of the two phi plus psi is also an element of this vector space. Also, any physical state multiplied by a complex number is again part of this vector space. Furthermore, this operation, which we call addition, should be associative. That means that phi plus psi and then plus chi is equal to phi plus psi plus chi. And addition should also be commutative. Phi plus psi is equal to psi plus phi. Another thing that is a requirement for a vector space is that there exists a zero element. So in quantum mechanics, this is known as the vacuum state. This is part of the Hilbert space, and if it is added to any physical state, it does not change it. Right? Then we should also have an additive inverse. This means that for every state in the Hilbert space, there must exist a state, let's call it minus phi, such that phi plus minus phi gives us the vacuum state. So this state also belongs to our vector space. The rest of the properties that define a linear vector space is that A plus B times a state phi should be equal to A times phi plus B times phi. And A times phi plus psi should be equal to A phi plus A psi. What am I forgetting? AB times phi should be equal to A times B times the state phi. And finally, the number 1 times any state should just give us the state itself. So any set of vectors or states psi is a linear vector space over a field, in this case, the field C of complex numbers, as long as these properties hold. For example, if you study a particle in a one-dimensional box or a well, you know that if you quantize the system, you will get a tower of physical states. And the Hilbert space will be spanned. It will be spanned by a basis of states that is like this. So all the states in the Hilbert space will be linear combinations of the states P, and I label here P the momentum of the states, with P being any integer times pi over L, where L is the dimension of this box. This is an example of a Hilbert space. And this also takes us to the idea of a basis. So this set of states labeled by their momentum P, where P is any integer times pi over L, is a basis for our Hilbert space. Yeah. So the formal definition of a basis would be a set of vectors that spans our vector space. Let me write this. A basis, it is actually a minimal set of vectors that span the linear vector space. What does span mean? Can anyone tell us? A set of vectors that spans the whole vector space, what would that mean? Any other vector in the space. Good. An equivalent definition of a basis is that it is a maximal set of linearly independent vectors. And a short reminder of what linearly independent vectors means. Let's say that we label our linearly independent vectors as states I, where I goes from 1 to anywhere, basically. Let's say it goes up to n, if this is a finite space. Then if we demand that a certain linear combination of these vectors is equal to 0, where these AIs are just numbers, this must mean that all AIs are equal to 0. And you can check that these two definitions are equivalent. Okay. Another thing that, yeah.
Is your linear combination always finite?
No, because for example, in quantum mechanics, usually you may have, you will have infinite dimensional Hilbert spaces. For example, here this is in your basis you have an infinite number of states. So this will hold even if it holds for every n, for n going up to infinity.
So that is why it's not linear vector space. So linear vector space, you have only finite sum. You need Hilbert space to go to infinity. So Hilbert space is something a little bit more than linear vector space. But you can think about it like that. But you are only infinite series if you have Hilbert space.
Thank you, David. Yes, but I think that for our purposes, we don't need to formally define the Hilbert space here, I think. Okay, so the next thing I wanted to talk about was a scalar product. And a scalar product is a map from the space times the space to the field of to our field. So in this case, it will be a map from H cross H to the field of complex numbers. Usually we use brackets to denote this. So this, excuse me. This denotes the scalar product between two vectors, but in usual Dirac notation, we write this as phi psi, and this is why we talk about the bra and the ket. Now, a scalar product should satisfy three properties. If you invert the order of the vectors, the result should be the complex conjugate of your original one. So phi psi is equal to psi phi complex conjugate. Scalar product of phi with a linear combination of psi and chi should just give us a linear combination of the two scalar products. The scalar product between the zero vector or the vacuum state should be equal to 0, and the scalar product of any other vector with itself should always be greater than 0. This is the problem. Well, in quantum mechanics, of course, scalar products are tied to the idea of probabilities. So the scalar product of a state psi with itself will give us the probability of actually finding our system in this state psi. And a vector space with a well-defined scalar product on it is known as an inner product space. Did you want to say something?
No.
Okay.
I'm just smiling because at some point we might talk about, in quantum field theory there are Hilbert spaces on which the scalar product can have norm 0.
Okay, yeah. That will come. Okay. Now, I guess you already know that an orthonormal basis is one for which, and now let me change my notation for basis and let me use EIs. This is an orthonormal basis if the scalar product between two vectors in this basis is equal to delta ij. So any two vectors which are not the same vector are orthogonal to each other, and the vectors are normalized to 1. And of course, we also talk a bit about the dimensionality of vector spaces as the number of vectors in the basis of our space. So if this is a basis and this goes up to infinity, then this is an infinite dimensional vector space, whereas if it terminates at some n, the dimension of this vector space, let's call it V, will be n. Okay, now let's talk about dual spaces. A dual space is basically a set of operators taking you from your vector space to your field. So if V is some vector space, then V star will be the dual vector space. And it will just be the set of maps, let's call them rho, that take you from V to the set of complex numbers. For example, the scalar product is one such map. So the scalar product belongs to this dual vector space. In this sense, we also think of bra vectors to belong to the vector space as well. So we write that phi belongs to V star because this thing, the scalar product between phi and psi, should be thought as, let me write this, phi of psi, and this is the scalar product between the state phi and psi. So the ket belongs to your vector space, V, and the bra belongs to the dual vector space. It's actually a map from V to C. Questions? Okay. Now, you know that in quantum mechanics, you're always dealing with operators acting on your states. And a linear operator is one that, by definition, acts linearly on your states. So a linear operator A would be one which, acting on a linear combination of states, would just give us A times the operator acting on the first state plus B, A acting on the second state. How about the adjoint operator? this is defined as, it is defined in this way. If you take the scalar product between phi and the state A psi, A acting on psi, then this is equal to the scalar product of psi times the adjoint operator acting on phi complex conjugated. This is the definition of the adjoint operator. Now you can check that if I define chi as A acting on psi, then the bra of chi will be bra of psi times the adjoint operator. And this is one of the things that I will ask you to show later on in the tutorial today. Another useful relation that you will come across in quantum mechanics is that if you have a basis EI, then you can always write the unity operator 1 as a sum over all I of EI times EI. And you can check indeed that this thing acting on any state psi, or let me write it more formally, this thing acting on any state psi will give you back the state itself. Okay, now let's talk about representing states as vectors and operators as matrices. So we usually represent every state with a column vector. We write phi as phi 1, phi 2, phi n, if this is a finite dimensional vector space, which means that in a certain basis EI, this vector is equal to the sum over I of the elements phi I times the vectors in the basis EI. Similarly, we associate the bras with line vectors. And then we can write the scalar product as the sum over i's of phi I star phi I. And we can just do the multiplication of this line vector with this column vector. Similarly, linear operators are usually written as matrices. So if I have a linear operator, say A, I can define a matrix with elements Aij equal to the scalar product of the basis vector Ei with A acting on another basis vector Ej. This will give me an n by n matrix. Okay. Having talked about operators, let's talk about eigenvalues and eigenvectors of operators too. And let's go back to quantum mechanics, where you're usually looking for eigenvalues and eigenvectors of your Hamiltonian. So this is an operator, H. And if psi is an eigenvector of H, then H acting on psi will give us back a number E times the same vector again. So this is an eigenvector. And this is the corresponding eigenvalue. The set of all the eigenvalues of a specific operator is called the spectrum of this operator. Representing operators as matrices gives us an easy way to find their eigenvalues and eigenvectors by solving what we call the characteristic equation. Right? And I'm guessing that you're all familiar with this. Yeah? Okay, good. So first we solve this equation and we find what the different values of the eigenvalues are. And then we plug them into this equation and we actually solve for the eigenvectors. Let's call them psi i's. Okay. Some interesting operators are Hermitian and unitary operators. So let's start with the definition of a Hermitian operator. this is one which is equal to its adjoint. It's a self-adjoint operator. And such operators have to describe all physical observables in quantum mechanics. Why is this? Because physical observables in quantum mechanics are things that we can measure, so they must be eigenvalues of a specific operator, say this operator H. And how do we measure them? We measure this thing. That gives us, of course, E times the scalar product of psi with itself. Now, since this is a physical observable, E has to be a real eigenvalue. Which means that E is equal to E star, and therefore the complex conjugate of this scalar product should also be equal to itself. But we know that this thing is equal to the scalar product between psi and the adjoint operator with psi. So H has to be equal to the adjoint. So Hermitian operators, they have real eigenvalues, and this is why they are very useful in quantum mechanics. Furthermore, let me write this. Wait. So Hermitian operators, they have real eigenvalues. And another interesting property of theirs is that they also have orthogonal eigenvectors. And I think I will leave this for you to check. And this is, again, very useful in quantum mechanics because, for example, when we quantize a particle in a one-dimensional box, then, as I said before, we find this spectrum of states. Basically, we solve this equation. And then our solutions are vectors that are orthogonal to each other, and they can actually be a basis for our Hilbert space. Okay, how about unitary operators? These are also very important in quantum mechanics because they preserve probabilities. That's why we always talk about unitary evolution in quantum mechanics. By definition, a unitary operator is one for which u dagger is equal to the identity operator. So if we start from a state psi and we act on it with a unitary operator, this takes us to chi equals u times psi. And now what is the norm of this state? Chi scalar product with chi gives us psi u dagger u psi. And if u dagger u is equal to the unity operator, this is just psi psi. So the probability of finding our system in the state chi is exactly the same as finding it in the state psi. For example, a unitary operator that you often come across in quantum mechanics is the exponential of minus I times the Hamiltonian times t over h. Why do we need this? Because when we solve Schrödinger's equation, for the time evolution of a system, we actually find that after some time t, we will evolve from a state psi to from a state, let's call the initial state psi naught, and we will go to psi equals minus I h over h bar times t. This is a unitary operator. You can check that its adjoint is given by e to the plus I h t over h bar, and that u dagger is equal to 1. It's easy to see that as Hermitian operators have real eigenvalues, unitary operators have unimodular eigenvalues. In other words, if, say, lambda is an eigenvalue of u, then lambda squared is equal to 1. And because I'm going faster than what I thought, and I also have the feeling that I'm becoming boring, I think that one of you can come up here and prove this. It's very easy. Don't make me point, just, yeah. Thank you. Yeah, and this is just equal to that. Yeah. Okay. Thank you very much. I'm not sure that this made it much more interesting, but at least it was something different. Okay, so wait a second. Well, actually, we even have time to prove that unitary or Hermitian operators also have orthogonal eigenvectors. So why don't you take 2 minutes to think about how to prove this, and then someone will do it for us. Either Hermitian or unitary, pick one. You gonna come? Thank you.
So depending how particular we want to get, we do have to assume that the eigenvalues are non-zero, which is okay because it's invertible. But otherwise, let's see. Two sets of eigenvalues. So then you want to figure out if this is going to be zero. It's also equal to 2. So that means that if these are non-zero, this has to be 0.
Because they are distinct. Because
Or if they have to be 1 by some weird chance.
If lambda 1, lambda 2 is 1, we already know that this is 1. Yeah. So which would have to mean that lambda 2 equals lambda 1. Yeah. If you have degenerate eigenvalues, that would be degenerate eigenvectors.
Well,
I mean,
so if the two eigenvalues are the same, that's fine because then you just have this, which is 1.
So that
actually, you can't guarantee that they're orthogonal.
Okay, so let me be more specific here and say that they have orthogonal eigenvectors corresponding to distinct eigenvalues. Okay, and the same thing holds for Hermitian operators. Okay, first of all, are there any questions up to here? No? Okay, then, since I am mostly done with what I wanted to talk about today, let me just mention a few things that I didn't talk about them here explicitly, but you should know them. So that would be how to diagonalize matrices. And basically, all the things I'm going to put in this list are related to each other. So also similarity transformations of matrices or operators. Changes of basis. And also orthonormalization of basis. In other words, if you are given one basis, you should be able to know how to change it into one which is orthonormal. Also, you should be able to write operators in different bases using always similarity transformations. And you should also know how to diagonalize a matrix. So you should, these are things that you will be using throughout the year, I guess. You have to know how to do it. If you're given a matrix, as long as it's diagonalizable, you should be able to do it. Yeah. This is where I can stop for today, if you don't have any further questions. Yeah. I don't know if John, do you want to say something?